Let's learn postulates of quantum mechanics. The postulates are the fundamental assumptions on which quantum mechanics is based. A postulate is supposed to be self-evident, requiring no proof, employed as a basis for the reasoning. For example, Newton's three laws of postulates of classical mechanics. These postulates cannot be derived. Newton's laws are postulates and are believed to be correct for macroscopic systems based on agreement with the experiments. The postulates of quantum mechanics also cannot be derived. They too are believed to be correct for both microscopic and macroscopic worlds based on agreement with experiments. The number of postulates differ from one book to another book. Some are combined. Here we are going to discuss 4 postulates. Postulate refers to the fundamental assumptions or basic principles that form the foundation of the theory. These postulates are the starting points from which the entire formalism of quantum mechanics is built. They provide a set of rules and concepts that describe the behavior of particles at the atomic and subatomic levels and allow us to make predictions about their properties and interactions. These postulates of quantum mechanics outline the key concepts and rules for representing the following points. So we are going to discuss 4 postulates. The first postulate says about the wave function, which is nothing but quantum states. And the second postulate brings out the fact of performing measurements to obtain the observable values upon measurements. And the third one goes with predicting the outcomes, which is nothing but eigenvalues of those measurements. And the last one that we are going to discuss is on the rules for calculating the wave function, which is nothing but eigenvalue equation. What we call this as time evaluation equation. They are the axioms upon which the mathematical framework of quantum mechanics is constructed. These postulates, along with other mathematical tools and principles, allow us to understand the behavior of particles and systems at the quantum level. They have been extensively tested and verified through experiments, showing incredible accuracy in predicting and explaining the behavior of subatomic particles. Postulates serve as basis of any physical theory and they cannot be proved, but one can prove the conclusion derived on the basis of postulates, which depends on the strength of the results. The collection of postulates in quantum mechanics is based on a huge number of experimental observations. So postulates of quantum mechanics, and we know that this is eigenvalue equation. The operator H, Hamiltonian operator, which operates on the function, will give us eigenvalue with a function. If both the functions are same, we call this as eigenfunctions. The first postulate refers the wave function. The second postulate refers the operator. Here it is a Hamiltonian operator. The outcome is the result, which is the eigenvalue of this equation E, which is nothing but expectation value. This is the third postulate. And the whole equation, eigenvalue equation, is nothing but the fourth postulate. And of course, we know that E can be expressed as I cross partial d by dt. So H psi equals I cross partial d psi by dt is a time evaluation operator. First postulate goes with like this. The first postulate says about the wave function. The state of the system can be completely specified by a wave function, psi of r comma t. So psi depends on both position and time. It has position coordinates r1, r2, r3, rn, and the time coordinate t. This is called a wave function or a state vector. It is a complex function of space and time. For example, psi star r comma t. All possible information about the system can be derived from this wave function. For example, when you take linear harmonic oscillator, so which refers one dimension, the wave function of any particle can be represented by a wave function psi, which depends on x comma t. When you take hydrogen atom, then So in 3 dimensions, this can be represented by psi, which depends on x, x coordinate, y coordinate, z coordinate, and time coordinate. See here. And so this is 3 dimension one. And when you take helium as a whole, there are 2 electrons in the helium atom. So each electron is represented by x1, y1, z1 coordinates and x2, y2, z2 coordinates. So as a whole, we call this a 6 coordinate system. The representation in which the wave function is a function of coordinate and time is called coordinate representation, which is denoted by psi of r, t. Whereas the wave function which is a function of momentum coordinate and time is called momentum representation. For example, phi of p, t. The probability of finding a particle is given by psi, the product of psi dx. For the entire system, which goes from minus infinity to plus infinity, it is given by integration minus infinity to plus infinity psi of x dx. The probability density, which is the product of wave function and its complex conjugate, is given then the wave function is normalized. If it is not normalized, then we can have minus to plus infinity psi star psi dx, which is equal to 1. If it is not normalized, we'll have to multiply it by a suitable normalization constant. For example, when it is not normalized, so the new wave function becomes psi divided by root 5 and psi star divided by root 5. Generally, if the wave function is not normalized, then it should be multiplied by a suitable normalization constant, a squared multiplied by minus into plus infinity psi star psi dx equal to 1. So here this is nothing but probability density, where a is the normalization constant. So this equation 1.1222 can be written as 1.123, and this is square integrable function. So we have squared the wave function and we have integrated. So square integrable wave function, and this value will be always less than infinity. That is, it must have a finite value. It implies that the wave function must be square integral function, and any physically acceptable wave function must be a square integral function. Only then it can be normalized. There are requirements for a wave function to be physically acceptable. They are: the first point, the wave function must be single valued at a particular point, since a particle can be found in one space at a given time. The wave function and its derivative must be continuous, since a particle cannot transfer from one space to another without passing in the path connecting them. The wave function must be finite in the particular region, and it must die out at infinity. The wave function that fulfills these requirements is said to be physically acceptable, well-behaved wave function. For example, when you take this diagram, and single valued and continuous at x equal to 0. For example, when you take the wave function psi equals a cos inverse 0, which is equal to 1, a cos inverse 2 pi, which is also equal to 1, a cos inverse 4 pi is also equal to 1. And it is not a single valued function, it is a multi-valued function. And this is, see, at x equal to 0, here it is a continuous. So this is a continuous function. For example, we take here at x equal to 0, it's a continuous function. When you take this diagram at x equal to 0, there is a discontinuity. So this is not a physically acceptable wave function. At x equal to some other point here, this is also there exists a discontinuity. So wave function is discontinuous. This is not a physically acceptable wave function. Which one of these is the most important characteristic of the wave function? You just find out which one is the most important. One, wave function must be single valued. Second one, wave function must be finite and continuous. And third one is the square interval function. The value of the square interval function is less than infinity, and which is equal to 1. And C is the much more important because this contains all the things. Show that y psi equals x squared is not a well-behaved wave function. For example, when you take the square interval function of this, we will have minus into plus infinity mod x to the power 4 dx, and the answer is infinity. But the answer should be less than infinity. So this is not a well-behaved wave function. Postulate 2. Postulate 2 denotes about observables, which are nothing but operators in quantum mechanics. Those operators are observables which depend on position and momentum. The dynamical variable is associated with the observable, which corresponds to the linear Hermitian operator. So operator must be linear, Hermitian. So the operator in quantum mechanics is derived from the Poisson bracket of the corresponding pair of classical mechanics. These operators are selected according to the rule as given by equation 1.124. So it has to follow commutative bracket, which is equal to I H cross Poisson bracket, Q comma R, where capital Q and R are the operators selected by the dynamical variables, small q and R. There are some observables in the classical form as well as the operators in quantum mechanics as given in the table. Some coordinates are there, x, y, z. They are in the classical form. Corresponding operators in quantum mechanics will be x cap, y cap, z cap. Function of coordinates, and this can be written as function of operators x comma y comma z cap. Momentum operator p, which is given minus I h cross del. Similarly, E can be written as E equals I h cross partial d by dt. And the component of momentum px, py, pz will be minus I h cross partial d by dx, comma minus I h cross partial d by dy, and minus I h cross partial d by dx. The potential energy is also an operator, which is nothing but V cap of x. Examples of observables. Operators representing some other dynamical variables take the following forms. For example, we take kinetic energy operator. So kinetic energy operator is nothing but 1 by 2m. Of course, kinetic expression for kinetic is nothing but p squared by 2m. In 3 dimension, we can write this as px squared plus py squared plus pz squared divided by 2m. So each component can be written in terms of operators exactly like this. So we can write this as minus h bar squared divided by 2m partial d squared by dx squared plus d squared by dy squared plus d squared by dz squared. Put together we can write this as del squared. So kinetic energy operator is nothing but minus h bar squared del squared by 2m. And of course we know that px squared equal to px multiplied by px, which will give us minus h bar squared partial d squared by dx squared. The potential energy operator is given by V cap. The Hamiltonian operator, kinetic energy plus potential energy, can be written as exactly as equation 1.128. So this is Hamiltonian operator. Similarly, we can go with angular momentum component operators using a commutative relation a comma b, which is equal to ab minus ba, and of course we know that px equals minus I cross partial d by dx. So L stands for r cross p. L is nothing but angular momentum, which is equal to r cross p. So this can be written in terms of components with a commutative bracket y comma pz, and using this rule ab minus ba, we can write ypz minus zpy. So we have minus I cross common out, we can pull it out. So we have minus I cross multiplied by that y is there. Pz is nothing but partial d by dz. Your py is nothing but partial d by dy. Similarly, Ly also can be written in terms of operators as shown here. Similarly, Lz also can be written in terms of operators as shown in equation 1.129. Operators in second postulate says that they must be linear and Hermitian. All Hermitian operators will have real eigenvalues. So linear means operator operates on the combined system, which is equal to operator operates on the individual system. See here, individual system. This is the first rule. And second rule is the operator operates on a scalar function with the wave function, which is equal to the scalar function. The scalar quantity can be taken out. So C A acts on psi. The example for the operator operates on the combined system is given on the right hand side. For example, when you take the operator d by dx operates on f1 plus f2, which is equal to df1 by dx plus df2 by dx. If this condition is satisfied, these operators nothing but a linear operator. For example, just take a function f1 equals x squared. f2 is nothing but e power x. separately you can do it. And similarly, differentiation of 10 sin x will give us 10 d by x of sin x. So here 10 is nothing but your eigenvalue. So let us consider two wave functions phi and psi. Just consider two wave functions. So this can be written as integration minus to plus infinity phi star a psi d tau, and we can write this as a complex conjugate of, I'm going to interchange this one. I'm going to interchange psi and phi. We can write this as the whole complex conjugate. See here, whole complex conjugate. If this condition is satisfied, then we can say that A dagger equals A. We call this as Hermitian operator. All Hermitian operators will have real eigenvalues. The eigenvectors corresponding to different eigenvalues of a Hermitian operator are orthogonal to each other. We call this as orthogonal eigenvectors. Physical observables, for example, position, momentum, energy, and angular momentum are represented by Hermitian operators because they will give real values. Postulate 3. Postulate 3 says about the eigenvalues. So in the lab, we are measuring something, we will get the outcome. So this is nothing but the outcome. The measurement of an observable would give one of the eigenvalues of the corresponding operator. For example, just take the eigenvalue equation. A operator operates on psi will give us lambda psi. Here lambda is the eigenvalue, which is the outcome of the experiment, which is the real value. Given operator may have several different eigenfunctions. Each eigenfunction is associated with its own value. So A psi n, n stands for 1, 2, 3, 4, goes on. So different set of different eigenfunctions, but each eigenfunction is associated with its own eigenvalue. Each measurement we may get different eigenvalues, but it is not guaranteed that we should get the same value. For example, we'll take a large number of measurements, n1, n2, n3, for which we are going to obtain some results lambda 1, lambda 2, lambda 3. Taking the average value of the observables experimentally, we can write this as lambda bar. So this is the average value, which is equal to n1 times lambda 1 plus n2 times lambda 2 plus n3 times lambda 3 divided by n1 plus n2 plus n3. Whereas in quantum mechanics, when the system is in the state described by wave function psi, the expression value or the average value of any dynamical variable is given by this expression, equation 1.135. So the expression value A is given as A operator sandwiched between psi and psi star d tau divided by a normalization psi star psi d tau. If the state function is eigenfunction of A, then A operator operates on psi will give us small a psi. You pull a small a out. So A and numerator denominator will cancel. We have A. So the expression value A equals A. The condition is if the state function is eigenfunction of A. If we take a large number of measurements, the average value of value will be A itself. In this special case, the state function is the eigenfunction of A. For example, we take the linear harmonic oscillator, which we'll be dealing later. The Hamiltonian for the linear harmonic oscillator is given by kinetic energy plus potential energy, and the eigenvalue equation is given by this, and the energy eigenvalue the expression for energy is given by En equals n plus of h bar omega. We substitute n equal to 0, 1, 2, 3, we will get corresponding energy eigenvalues. For example, when n equal to 0, we will have this value. When n equal to 1, we have 3 by 2 h bar omega. When n equals 2, we have 5 by 2 h bar omega. For example, measuring for n equal to 2, number of times, we will get the same 5 by 2 h bar omega. Then the average value is also 5 by 2 h bar omega, whatever may be the measurement. And this type of theory, what we call this is decoherence and measurement theory. When the wave function psi is normalized, then the expectation value is given by this expression. For the potential energy, the expression value is given by this expression, equation 1.140. We'll go for postulate 4, the time development of a quantum system. It describes how the quantum state of a physical system changes with the time. So postulate 4 mainly deals with the eigenvalue equation, and which is nothing but the time evaluation equation. The time development of the system can be studied with the help of equation of motion. It is a differential equation of the physical variable which describes the system, and it is given by I h cross d psi by dt, which is equal to h psi. Here psi of r is the eigenfunction of the Hamiltonian operator corresponding to the eigenvalue E. So we know that I h cross d psi by dt is nothing but in terms of operator, kinetic energy operator plus potential energy operator. So we can solve this equation. We can get the solution as psi of x comma t. The equation says how the state function evolves with time. The Hamiltonian operator determines how the state function changes with time. The time evolution of the quantum system is governed by the Hamiltonian operator. Hence, the Hamiltonian operator is very, very important in quantum mechanics. Now, what are the consequences of postulates? For in normalized wave function, we know that this is given by the expression value of any observable is given by this expression. That's the operator sandwiched between normal wave function and its complex conjugate. Suppose if the state function is eigenfunction of A belonging to the eigenvalue, then we can write A psi equal to small a psi. You pull small a out, so this will be equal to 1. So we'll have A. It implies that the expectation value of A operator, which is nothing but small a. This observable exhibits a sharp value, that is A. If the system exists in a state such that an observable exhibits a sharp value, then the state is called the eigenstate of that observable. Any wave function of the system psi can be expressed as a linear combination of psi I. So we know already capital psi equals sigma over psi I, Ci psi I. So this is the linear combination of small psi to form a complete set. I'm going to multiply on both sides by psi I star. So psi I star, psi I will give me 1 integrating after integrating. So I can get the expansion coefficient Ci equals integration psi I star psi d tau. We are going to use this expression later. Now we know that psi equals sigma over Ci psi I, psi star equals sigma over j Ci star psi I star. Now we know that expectation value is given by this expression. Now we shall substitute for psi star here, substitute for psi here. We will have this. We can pull the expansion coefficient constant out. We will have this expression. A operator operates on psi I will give us small ai psi I. So I can pull this ai out. If I equals j, the condition goes with psi I star psi I d theta, which is equal to 1. So we'll have Ci mod squared ai. And of course we know the expression for Ci here. You just substitute here. This is nothing but the inner product, which is nothing but the probability amplitude. The inner product which says the finding the system in the final state once you make the measurement on the initial state. When the system is in eigenstate psi I, the probability occurs at the value ai in the measurement of A. The expectation value is the sum over all possible eigenvalues, which is nothing but ai, with the probability density mod squared, that is integration psi I star psi I d tau. The another very important consequence of postulate is stationary states. Suppose we are going to consider the Hamiltonian. In the Hamiltonian, suppose you are going to consider potential energy is time independent, that is, it does not depend on time. Then there exists some special cases, what we call this stationary states. It implies that there is no transition between the states. Suppose you are going to consider this is as a wave function at t equal to 0. After some time, this will behave exactly the wave function behaves like this. See here, psi of r comma t. And suppose in special case, when t is constant, then the psi of r exactly go with psi of r itself. See here. And what of the time evaluation equation, which is nothing but I get cross d psi by dt, which is equal to kinetic energy plus potential energy. The solution of this equation is nothing but psi of r comma t, which is equal to psi of r e power minus e by h cross t. We have already studied in using separation of variable techniques. So in that case, suppose you are going to multiply the complex conjugate part and the normal part, then we'll have mod psi squared, which is equal to sigma over n a n squared multiplied by psi n of x squared when n equals m. And of course, this will become 1. We have psi n squared multiplied by psi m squared. If n equals m, then we can say psi n of r multiplied by psi n of r will have this. The probability does not change even though the system is changing here. See here, left hand side depends on time, whereas right hand side does not depend on time. It says that the probability does not change even though the system is changing with the time, and the probability amplitude remains the same at all times. So what we call this as stationary states. And of course, stationary states exist around the orbit of the nucleus. For example, when you take the electron's orbit, these are all standing waves. So all the electrons are at the stationary states when A0 is the Bohr radius. And the angular momentum of the electron in the orbit is quantized, and it was predicted earlier by Niels Bohr in the year 1913. Whereas then after some time, it was verified by de Broglie in the year 1924. So de Broglie explains Bohr's postulate of angular momentum, which is quantized. We know that just now we said the stationary orbits which are revolving around the nucleus, so which is equal to 2 pi Rn equal to n lambda. And of course, we know that lambda equal to h by p. You substitute here lambda h by p, which is equal to n times h divided by, instead of p, you substitute MeV, mass of the electron multiplied by V. So cross multiplying, you will have MeVRn, which is equal to n multiplied by h divided by 2 pi. H divided by 2 pi is nothing but h bar. What is MVR? MVR is nothing but angular momentum. So L equals n h bar. So L is quantized. With this, we will stop here. We'll see in the next class.